Today's lesson is on continuous probability density functions and a little bit with normal distributions. As we talked about in the last chapter, we looked at discrete random variables, took a quiz on Friday, so you should get those back soon. But today we're going to take a look at continuous random variables. So difference between discrete and continuous. Discrete, remember, is things we can count. Continuous is things we have to measure. Okay? And a probability density function is a function used to specify the probability distribution. Okay? And it's called a probability density function. Probabilities are found by calculating areas under the probability. So again, here's that calculus coming back. Area under the curve over a particular interval. Okay, here's the probability density function. Notice, okay, it's a function evaluated through an integral. Okay, function evaluated through the integral. And it goes from, that's when f of x is greater than 0, we go from a to b. So pretty simple concept there, probability density function. Probability that its variable x lies within an interval. So for the second part of this, okay, same thing from c to d. So basically saying the same thing, except using x and f of x are a little bit different. All right, so going on. Since the variable is continuous, we can recognize probability of x is any exact value is 0. Instead, we can only measure probability of x being a particular interval. So we identify it over a particular interval, whatever that interval might be. A particular interval, whatever that interval might be. The mean, or mu, or expected value of x of a continuous probability density is defined by x times the function. X times the function. And then we do the integral of that. So the mean, or expected value, is x times f of x. And then evaluated over that integral from a to b, or c to d, whatever the function is. All right, so going on, here we have a function, a probability density function. Check that the above statement is true. How do I check that the above statement is true? Okay, I simply take a, I'm going to take 1/2 of x dx from 0 to 2. I take 1/4 times that. Okay, so I do the integral. I have to add 1 to the power, take it times 1/2. 1/2 times 1/2 is 1/4 x squared, and it has to equal 1. Okay, the probability density function. All probabilities have to add up to be 1, so its density under that curve is 1. So we know that it's true. Second part, I have to find the probability from 1/2 to 1, so the cumulative probability from 1/2 to 1. So I write the integral, and then I have to do the integral and evaluate it from 1/2 to 1, from 1/2 to 1, which is 1/4 minus the 16th equals 3/16 when I evaluate it. So I have to plug 1 in, 1 squared is 1, that's the 1/4. Then I put 1/2 in, and that's going to give me a 16th. 1/4 minus 16th is 3/16. So the area under that probability from 1/2 to 1 is 3/16. And then continuing, part C is asking us to find the mean of the distribution. So finding the mean of the distribution, mu, I simply take x times the function. So I take x times the function and evaluate it at that point, but to do that I have to do the integral. And that's what I do here. I've done the integral, so I'm going from here over to here. So 1/2, I have to add a power. So I multiplied them. So I took this, multiplied it to get to here. Now I'm going to do the integral. So I add 1 to the power, take it times 1/3. That's where the 1/6 comes from. X to the third evaluated from 0 to 2. So the mean is 8/6, or 1 1/3. Continuing, normal distributions. A normal distribution is like a bell curve. Okay, a bell curve. Normal distribution. The mean, mu, is here. Okay, mu. And then the distribution, or the standard deviation, is plus or minus 1 each way, and so on. 2 standard deviations, 3 standard deviations, etc. Okay, so for a normally distributed probability density function, this is an equation we can use to find it, where, okay, and here's, we have sigma squared is the variance, sigma is the standard deviation, mu is the mean. Now this is of a population. Notice it's talking about parameters. Okay, statistics deal with a sample. Parameters deal with a population. So these are talking about the population. Okay, and we continue. This probability density function winds up representing this. So this is a point of the mean and then whatever function is created when I do this. So a normal curve. We have that point, and if you figure out, if you put in the mean, which we can find by using a probability density function, I can plug that in to this function and get the solution. Okay, so it's simply a point. You can find the y value by plugging x in. All right, continuing, characteristic of a normal probability density function, the curve is symmetrical on both sides of mu, or the mean. As x is plus and minus the normal curve approaches an asymptote, the x-axis, f of x is always greater than 0. The area under the curve can be defined by, from infinity to positive infinity, if it's a total of 1, physical approaches 0, and all probabilities have to add up to be 1. More scores are distributed closer to the mean than farther away. The results are wind up with a typical bell-shaped curve. So we continue. This is all the proof of all of those common concepts, which is really what we're going to be demonstrating. Now, a point of inflection. There are points of inflection. So if you recall, points of inflection refer back to our calculus, our derivatives, second derivatives, things like that. So we'd have a horizontal point of inflection at the peak. These are non-horizontal points of inflection, so identified by the second derivative, so something else you'll need to think about. But those are created. We can find them by using some calculus and second derivatives, but we can also find them if we know the mean. We can find them by adding or subtracting the standard deviation. So this is the average, the mean, plus 1 standard deviation. And this is the mean minus 1 standard deviation. And we can continue going, expanding that out. And this is a breakdown of what all those what all of those are. We broke it down last year as just whole percentages. Now we take it a little bit further. 68.26% of the data lies within 1 standard deviation. So each of these is 13.13%. 13.59% falls in this second category, plus or minus. So total, that's 95.44% of the data. And 99.74% of the data falls within 3 standard deviations of the mean. So the total of that. So this piece is 2.15, and this is 2.15. And then there's 0.13 out on the end, which we don't talk about because then it has to add up to be 1. So this is a distribution of the probabilities, and you'll need to know this information. All right, so chest measurement of an 18-year-old male footballer are normally distributed with a mean of 95 centimeters, a standard deviation of 8 centimeters. Okay, find the percentage of footballers with chest measurements between 87 and 103. So if I have a standard deviation or a normal curve, and I know the mean is 95, and it's 8 centimeters, so this is going to be 103, and this is going to be 88. Or 87, sorry, I can't subtract, 87. 87 to 103, that is going to be these two middle pieces, so that's 68.26%. 68.26% of the data falls there. From 103 to 111, well, that would be between these two, and that's from 1 to 2 standard deviations. If you look back, that is going to be 13.59%. And continuing, find the probability that the chest measurement of a randomly chosen football player is between 87 and 111. So what did we just add? We just took 68, this middle part, 68.26 plus 13.59, whatever that equals out to be. So pretty simple concept. It's 34.13 here, 34.13 here, and 13.59 from there, from 87 to 111. Find the value of K such that 16% of the chest measurements are below K. Okay, so we have to find out what values are going to be below K. Now, we have to have 16%. So only 16%. Okay. Okay, so here, this is 50% of the data over here. This is another 34%. That's 84% of the data is between there and there. Correct? Agreed? So find the value of k so that 16% of the data is below that value. What value, that's approximately 16%, is this value k? Well, we already figured it out because we went down. Okay, it's 95 minus 1 standard deviation of 8 is going to be 87. So k is 87. It's pretty simple math. Just have to be able to remember and organize and process those pieces. So those are the two things we need to be able to finish on Monday is the continuous probability density function and then also some normal distributions. Have a great weekend. We'll see you Monday.